0.5, and we're going to just continue to extend the maximum, grade or the maximum for our directional derivative. And so again, we're going to be able to find, how steep our grade is along a path, and we're going to be able to find basically the rate of that path due to directional derivatives. So what we're going to do first is, in order to find, the directional derivative, I'm going to need my gradient of our function xy. And so let's go ahead and do the gradient. So when I'm doing the gradient, again, I'm doing partial derivative of x and partial derivative of y. So when I look at my function to do the partial derivative, it looks like I'm just going to have 0.005 times 2x. So that's going to be negative 0.01x. And then for my partial with respect to y, it looks like I'm going to have 2 times 0.01 or negative 0.01, and I'm going to get negative 0.02y. And my point at this, where I'm starting, is going to be 60/40. So the gradient at 60/40 is what I'm looking for. And that's going to be equal to, and so I'm going to go ahead and just plug this in. I'm going to plug it in. I'm going to get negative 0.6 and negative 0.8 for my gradient at the point where we're starting. Now, the first part is we're going, so let's do A, is if you walk due south. So we're just going to walk straight south. So will you start to ascend or descend, and and at what rate? So for our directional derivative, we're going to go ahead and I'm going to take this of our function. So we're going to take our gradient. Let me just go ahead and rewrite this. The directional derivative of f of 60/40, and that's going to give me the gradient times the unit vector of I'm going in what direction now? I'm going south. And so if I'm going south, so I'm just going, and here I'm on an xy plane, so I'm just going south. I'm not going, west or east. So if I'm going straight south and I'm doing a unit vector, then my unit vector is going to be 0 for the x, negative 1 for the y, because I'm going south. And so now I'm going to go ahead and multiply. So 0 times 0.6 is 0. Negative 0.8 times negative 1 is going to be 0.8. So because it's 0.8, when I walk due south from where I start, 60/40, 966, we will ascend. Let me highlight this. And so that means that we will ascend at a rate of 0.8 vertical meters per horizontal meters. Alright, now let's do B. Again, we're going to do the directional derivative of our function. And so we're just going to do that with respect to our x value of 60, or not respect of our x value 60, y value 40. And so we're again going to have our directional derivative, and we're going to use it as a dot product of our partial, our gradient f times, in this case, we are walking northwest. So because we're walking northwest, all right, if I walk a value of, that's not west, that's east, northwest, all right, so say we can just pick any value in northwest. So I'm going to say, okay, let's just go negative 1 for the x, and then positive 1 for the y. that's our vector. But if I want a unit vector, I'm going to have to make sure that I divide by the magnitude of that, which is going to be the square root of -1 squared plus 1 squared. And so my unit vector is going to be -1/2, negative square roots of 1/2, 1 over squared, negative 1 over square root of 2, positive 1 over square root of 2. So that's the unit vector. So then our unit vector is just going to be -1 over square root of 2, positive 1 square root of 2. Now we go ahead and multiply. When we do this, we're going to have -1 times -0.6, which is going to give us 0.6, plus 1 times -0.8, which is just going to give us 0.8. So -0.6 minus, positive 0.6 minus 0.8 is going to be -0.2 over radical 2. And now that's just going to be an approximation of -0.14. So as we are traveling due northwest in our direction of the unit vector, we are going to descend at a rate of, so that's a point there, at -0.14 vertical meters per horizontal meter. Alright, we're almost finished. The last thing we're going to do is we're going to find in which direction is the slope largest, what is the rate of ascent in that direction. Alright, and so let's go ahead and find our, again, if we want to find maximum, we're just going to take the magnitude of our gradient vector. And so the magnitude of our gradient vector is just going to be -0.6 squared plus -0.8 squared. When we do that, we're going to get the square root of 1, which is just going to give us 1. All right, so the angle, so that is the direction of our slopes. Again, there's direction. And, well, I'm sorry, that's not direction. That's going to be our max. And now we want to find the direction. So the direction, the angle above the horizontal in which the path begins is given by tangent theta is equal to 1. And we solve for theta, we're going to get 45 degrees. Okay, and again, the angle above the horizontal in which the path begins. So what we're doing is we're just talking about, we have to be, above the horizontal, and whatever we get our magnitude, if we're ever looking for the direction, we would always use tangent, because that's going to involve, the direction of our x and the direction of our y. And so like opposite over adjacent, so that's going to always be tangent, and then tangent, if I do the inverse of tangent, I'm going to get the direction in which we went.